Good morning, everyone. This is Dr. B. Polaiah, working as a professor in the Department of IT, Institute of Aeronautical Engineering, Hyderabad. I'm very happy to share my today ELRV video that is on the importance of sharpening frequency domain filters. Here, actually, a topic which we have selected from the syllabus of image processing. Yeah, the image processing, which we understood from the previous slides and the previous classes, about to how this image processing we can be used as one of the processing tool for the designing of any type of image which we can convert into in our required nothing but development of particular and applications. So let we can have the same thing, how to understand the sharpening frequency domain filters. He is here towards to define such a sharpening frequency domain filters and how it can gives the how it can be play an important role in image processing. So coming to the one more important point is sharpening frequency domain filters is a filter which we can understand a high pass filter is used for passing high frequencies, but the strength of the frequency is lower as compared to cutoff frequency. Sharpening is a high pass operation in the frequency domain, nothing but as a low pass filter. It also has standard forms such as ideal high pass filter, Butterworth high pass filter, Gaussian high pass filter, and which can be extended in terms of edges and sudden changes in gray levels are associated with the high frequencies. Thus, to enhance such a frequency domain filters, which we can concentrate on sharpen significant details, which we can need it in terms of high pass filters in the frequency domain. So, let you can understand that the high pass filter how it is from the low pass filter is here. We are going to have to discuss that relation in between low pass filter and high pass filter by the help of a simple mathematical equation that we call as HP U comma V 1 minus LP of this, where U comma V are the Cartesian variables which help us to understand about the domain, that is frequency domain variations in terms of sharp frequency domain. So let we can take one of the example is here for the understanding of how why we want to understand for the sharpening filter is here. If you make a question, then let us understand one another. Here the original image which we are taking from the which is standard an image, and we converted into by applying Butterworth filter process and Gaussian high pass filter, ideal high pass filter, which can be visible here until up to in your required manner. But still, there are some disadvantages which we need to be concentrated on sharpness those filters of the process. So we want to process those filters of the process. We are going to use a simple mathematics are here. Those we'll get it from the high pass, that is the ideal high pass filter that we call simply high HPF. The high HPF cuts off all low frequencies of the DFT, but maintain the high ones that are within a certain what we call that are within a certain distance from the center of the DFT. So h of u comma v is nothing but 1 comma 0. That is, if u comma v is greater than d naught, or if d comma u comma v is less than or equal to d naught. So what we can understand here, what is the d naught is here? D naught is the cutoff frequency, which is we are keeping in terms of towards to make the process which we are previously we have gone through about Butterworth, the Gaussian, ideal, high pass filters. So we want to increase that towards to requirement in between one level to the high level. So from 0 to you are maximized that process, which we can be radial cross section process, and we understand that we achieve this. So how we can raise this frequency levels in terms of sharpness? We may be defined m value and n value based on the your selected matrix of the image, either 2D image or a 3D image. This is the m by n, actually m by n values. So this m by n values, which is we are simply we are keeping on to connect for the processing. Okay, so in terms of your required manner which we can be achieved. So coming to the sharpening frequency domain filters, or which we are keeping on ideal high pass filters sets to 0 all frequencies inside a circle of radius d naught value, which is the frequency value while passing without attenuation all frequencies outside the circle only. So attenuation also we need to be concentrate for the frequency value which can be vary in terms of angular frequency, but it is not be concentrated here which we want to sharpen on. By the seeing these below figures, okay, the applying IHPF with cutoff frequencies in between 15, 30 and 80 values, which can be understandable original image resultant of IHPF with cutoff frequencies. So these values 15, 30 and 80 respective values of the image, which we can be vary in terms of A, B, C, D values. So from the B, D to D, the resultant of the image process, which you can understand here in terms of ideal high pass filter with the help of cutoff frequencies. So based on this cutoff frequency of D naught variations, we may be achieve your required image. So coming to the, we extend that HPF effects in terms of ranging effect, ringing effect and edge distortion. The distortion is here distorted, thickened object boundaries. Okay, both effects are declared. Both effects are decreased as the cutoff frequencies increases. Okay, so Gaussian high pass filter is the Gaussian high pass filter is Gaussian high pass filter is with cutoff frequencies at distance d naught is defined as in terms of mathematics, which we can be used here towards to define this d naught value. I said here this d naught will play a major role which we are varying in terms of keeping on concentrated values. So this will be saturated. If it varies, then it will become your S curve. So what do you mean to understand is here? So you understand is here the important of radial cross section, which we are concentrating in terms of sharpening your frequency domain filters process. So simply we can extend our discussion on sharpening frequency domain by the help of simple inverse transformation of natural log, which is exponential process, that is s of x comma y, where I dash of x comma y plus r dash of x comma y. G of x comma y is equal to exponential of s of x comma y. Exponential of I dash x comma y is nothing but which we are going to be used in terms of your required process. Okay, so here you are applying this what we call I naught of x comma is elimination, r naught comma x comma is a reflection of the component of the particular output of an image, which is right now we are keeping into the one simple method is based on a special case of class of systems known as simply we call as homomorphic system. Homomorphic system. So homomorphic system is simply we define as overall model in the block diagram, which can be looked here. We are processing the same mathematics processes here with in terms of you are taking your objective function of x comma y, and which we are processing in the pre-processing of logarithm and fast Fourier transform will apply to convert into your required what we called which we discussed in the earlier class, that is restoration of the image, and that degradation of the process which we can be apply in terms of inverse fast Fourier transform. Then we'll get obviously a required what we call f of x comma y to g of x comma y we will be transformed, which we are understand in terms of exponentially process. So coming to the such a filtering in the frequency domain, which we are going to be have here, such a sharpening happen by the modification of such a values of your mathematical values, that p is equal to 2m minus 1 is the q equal to n minus 1 is the one value which we are going to be concentrate on. Arrays are of same size if functions of f of x comma y and h of x comma y are of size m by n and kxl respectively. If the p value which we want to keep on to increases are zeroth pad h and f, the pad both to at least radix 2, yeah, f of t requires power of 2. For example, if m equal to n equal to 512 and k equal to l equal to 16, p equal to q equal to 1024. So resultant in linear convolution which extract the your m by n values. What are the m by n values? Which are we are keeping on from the your image, which you are consider as another example. So you can also concentrate such a sharpening filtering process, especially in filtering frequency domain. We are using here discrete Fourier transform, and such a process simply will apply these 5 steps. Step 1: multiply the input padded image by -1 to center the transform, and second step, compute your objective function in terms of u comma v and apply the DFT of the image from the step number 1. This is step number 1, and we'll go to have the step number 3. By the help of filter function, you may multiply your object function and get the h of u comma v. It is the degradation image we call as a fast Fourier transform of a restoration image. And the fourth step, which we concentrate on, compute the inverse DFT of the resultant from the step number 3. Then we'll obtain the real part of the result, in which we are concentrating in step number 4 as obtained in step number 5. So step number 6, multiply the result in 5 by -1 given the filter h of u comma v, that is filter transfer function or filter function in the frequency domain. The Fourier transform of the output image, filter image, is given by g of u comma v is equal to h of u comma v f of u comma v. It is the convolution formula. From the step number 3, we'll get the your array multiplications. From this, we're going to get your required transformation of g of x comma y is simply the inverse Fourier transformation of g of u comma v. So, what are these steps are help us to make your frequency domain filtering process in terms of smoothing, sharpening. So coming to the you extend that discrete function m in terms of m points, the Fourier spectrum and discrete function based non-zero points and Fourier spectrum, how it is will be vary in the m points, negative and positive. Okay, so for example, you taken this k points values and based on the m request, and 2k point that is extended, then the sharpening of the your what we called your expected sharpening frequency domain filters output will be attained. So for example, let you can take in between low pass and high pass filter differences also is here, and which one is showing your best. So low pass filter will be allowed maximum the frequency domain will be allowed from only in between 1 hertz to some minimum 1 kilohertz. Whereas this, it is started high pass filter itself. The range of high pass filter frequency will be start minimum from kilohertz to minimum or maximum will be getting the gigahertz. So these are the variations. So based on these frequency values, we can also see that what we called dimensionality of the filter function will be vary based on the variation of this range of frequencies. and we can see the view also, how you are processing that values in terms of resultant of high pass filtering the image. So coming to the, we extended that information which we want to define finite impulse response filter, we call the FIR of h of u comma v. Here we are applying such a convolution f of x comma y into h of x comma y. We will get obviously your f of u comma v, which you are applying FIR. The spatial domain processing in general is faster than frequency domain processing. In some cases, it is desirable to generate spatial domain mask that approximates a given frequency domain filter. The following procedure is the one to create these masks in a least square error sense. So recall the filter processing again in terms of frequency domain, which is more supported of filter and function, becomes a convolution of the function and filter in the spatial domain process. So coming to the, we extended still more filtering in the frequency domain, which we consider under the sharpening of the frequency domain of the filter process, which we apply. So far we concentrated fast Fourier transform and inverse Fourier transform, even a finite inverse Fourier transform. Also we concentrated even FIR we concentrated. So what we want to understand from here, extendedly, this Fourier transform is the one where we can extend towards to have the shortening of filter process in terms of Fourier transform application, Fourier transform methodology. We'll get n by n convolution mask h cap. So by the help of this frequency domain of the frequency values which we varying in terms of x comma y of a particular your image x comma y objective function, will get your required objective of the coefficient of h comma x comma y, such that error will be minimized. How much error it will be minimized is mean square error, that is MSE. That is MSE. What we call MSE, mean square error. So this values we are going to be concentrated on towards to reduce the error and get your required output nothing but resultant image which you are based on applied of this Fourier transform will get 100% perfect. So after you consider this following filter transformation, which we are keeping on in terms of frequency domain, by the help of these frequency components of the m, n values variables, these m and n values are called from your basic matrix of given input original image, which we can apply in terms of notch filter. Since it is a constant function with a hole, that is a hole nothing but notch at the origin of the process. This origin of the process are varies in terms of m comma n values. You know, m comma n is nothing but which we define from the standard input image which we are varying in terms of matrix values of rows and columns. Those rows and columns values are vary with respect of pixels and intensity. I'm also extending one more important filtering process that we defined in earlier also and previous slide based information. This morphic, that is a homomorphic filtering process, which mathematically in terms of illumination and reflectance, as we are preparing your object function of f of x comma y based on these two, simply we apply here also when we are processing in a convolution way or in terms of fast Fourier transform way, we cannot expect same. Cannot be expected same. So to accomplish separability, first map the model to natural log domain, then take the Fourier transform of it, then we'll get your output which we are getting. So this completely process of filter function h of u comma v is as per the simple block diagram which we considered earlier. So of course, I'm very happy to extend here another what we want to understood from frequency domain filters. Already this complete basics information was repeated. So by the help of this low pass filter in processing, example we take high A is ideal low pass filter, and we got this cross sectional information which we discussed. Okay, so that is what we are important. And last but not least, I'm also extended here, that is smoothing frequency domain filters. We can see the falling effects of GLPF compared to IPL. So ILPFO. So inverse low pass filter processing. We are expecting 100% smooth filtering is usually in many applications. For example, best application is bridge small gaps in the broken characteristics by blurring it shown below. This is useful of the character recognition process. Of course, we started actually to introduce the smooth frequency domain filters by the help of Butterworth low pass filter only. But here, still we wanted to tune this D naught and D value to get your Butterworth more sharpness. With this, I want to conclude our discussion, which we are concentrated on the importance of sharpening of frequency domain filtering process, which we want to understand while we are processing your input image, which we consider as an objective function, to the output function as g of x comma y. So by the our discussion may understood perfectly, but still you wanted to refer some more textbooks, you can refer this list of references also. So I'm very thankful for your concentration on our discussion, and thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.